Welcome again to my classroom. We saw in the first session on lifecycle modeling that one of the critically important facets of asset management concerns the management of lifecycle costs of the assets under the care of the asset manager. This is then the second of the two videos on this topic. It covers a lifecycle analysis method developed by Paul Barringer, a well-known consultant in the maintenance world. The method first develops a general model for a certain lifecycle situation and then uses Monte Carlo Simulation to extend the method to cater for reality. If you have not done so, you are strongly recommended to view the Monte Carlo method video before viewing this one. We start by listing the reference for the work of Paul Barringer and David Weaver, which we base this session on. This resource is available on various internet sites. Now for some principles from this source. First, lifecycle costs are summations of cost estimates from inception to disposal. So it takes estimates of income and costs over the life cycle and use that to analyze. Second, lifecycle cost analysis helps engineers justify equipment and process selection based on total costs rather than the initial purchase price. Thus, the total picture is assembled using the purchase price and all estimates and known costs expected over the life cycle. Third, usually the cost of operation, maintenance, and disposal costs exceed all other costs many times over. This is why it would be silly to take the purchasing price only in making the choice between different equipment options. Fourth, the best balance among cost elements is achieved when the total lifecycle cost is minimized. We refer to Landers 1996. This is a statement from Landers, Product Assurance Dictionary. As with most engineering tools, lifecycle cost provides best results when both art and science are merged with good judgment. Procurement costs are widely used as the primary and sometimes only criteria for equipment or system selection. This single-purpose criteria is simple to use, but often results in bad financial decisions. The results may be damaging to the financial well-being of the business enterprise. The thing is, procurement cost is only the tip of the iceberg. Lifecycle costing is a very important tool for many applications. Lifecycle costs can be profitably used for affordability studies, equipment selection studies, design trade-offs, repair level analyses, and warranty and repair costs analyses. Two alternatives are being considered for installing an online spare pump in parallel with an existing ANSI-grade pump to avoid outages that have plagued a chemical plant. The parallel pump, which will be operated every other week on a rotation schedule and whenever pump failure occurs. This is an incremental investment or operation, will save on average $12,000 per year in out-of-pocket production losses for product which cannot be shipped during the outages. Pumps under consideration with expected 20-year lives are firstly another ANSI pump at $8,000 installed cost, second an ANSI enhanced pump at $18,000 installed cost, and three a do-nothing situation. Which course of action should we recommend using the concepts described above? Consider alternatives given below. By the way, year 0 is now, and year 1 is next year. Before doing any calculations, one must get all the relevant information together. The following is a stepped approach for doing that. The total process looks as is shown. There are 11 steps shown, starting with defining the problem and ending with the profitable use of the analysis. The cost consists of two components: the acquisition cost spent during the onboarding of the system and the sustaining cost spent to keep the system productive. In principle, the costs included in lifecycle analysis are then made up of these two components. Some of the costs may be spent only at one point in time, while others may be recurring. See the recurring acquisition cost in the acquisition cost tree. All acquisition costs are not simply non-recurring costs. Lifecycle cost requires facts which are driven by data. Most engineers are of the opinion that they lack data. In fact, data is widely available as a starting point for lifecycle cost, as stated by Bloch and Geithner in a conference paper titled Simplified Lifecycle Cost Computations Applied in the Hydrocarbon Processing Industries in 1995. Follow the guidelines for each of the 11 steps listed in the process chart as follows, based on the example. Step 1. Define the problem. A pump is operating without an online spare. At pump failure, the process shuts down and the financial losses are incurred as each hour of downtime results in a gross margin loss of $4,000 per hour of outage. Find an effective lifecycle cost alternative as the plant has an estimated 10 years of remaining life and is expected to be sold out during this interval. Step 2. Alternatives and acquisitions or sustaining costs. There are 3 alternatives. First, do nothing. Continue solo ANSI pump operations with 100 horsepower, 750 RPM, 250 PSI, 500 gallons per minute, 70% hydraulic efficiency, while pumping fluid with a specific gravity of 1. Second, add a new second ANSI pump in parallel, literally in redundant standby, which can be started immediately without the loss of production upon failure of the running pump. Alternate running of the parallel unit every other week to avoid typical failures incurred by non-operating equipment. The capital cost for the second pump is $8,000 plus $3,000 for check and isolation valves plus $2,500 for installation. Third option, remove this existing solo ANSI pump and replace it with a new solo API pump with the same performance as for the ANSI model. API pump costs $18,000 plus $3,500 for installation, and the installation will incur a 4-hour loss of production for connecting the new pump. Step 3. Prepare cost breakdown structures and trees for each of the 3 alternatives. Step 4. Choose analytical cost model. The model used in this case is contained in an engineering spreadsheet, which Barringer and Weber developed as an aid to using in the tutorial. This resource is available on various internet sites by typing in a search window Barringer Lifecycle Cost Spreadsheet. Step 5. Gather cost estimates and cost models. This is quite an involved section where all the details are assembled. It is necessarily so that the more thorough the collection process, the better the lifecycle cost model. For this tutorial, the details have been shortened with enough just information described to show the trends. Alternative 1. Alternative 1 is the do-nothing case. The present pump is left as is. Capital cost is 0, favoring the retention of this pump. However, some of the other costs are quite high. We lose $4,000 per hour when this pump needs repair. Annual power cost is $16,500. Pump seals need to be replaced once in 3 years with 8 hours of downtime, crew costs of $100 per hour, and material costs of $1,500 per seal, plus $300 per incident for bearing replacements, and so on. The annual acquisition costs are 0, but there is a disposal cost of $3,000 in year 10. The sustaining costs are shown in the last figure and comes to $54,827 per year. Example calculations are shown for first the seal cost line, that's line 2, calculations for alternative 1. The other lines are calculated in the same way. Second, the reliability calculations for alternatives 1 and 2, that of alternative 3 is calculated in the same way. 3. the availability calculation for alternative 1. The availabilities of the other two alternatives are calculated in the same way. Alternative 2. This case results in pumps installed in parallel but operated as a standby redundant system, as the redundant components are not energized but are literally standing by waiting to be used when failure of the operating system is detected. Of course, the detection or switching device is very important for calculating overall system reliability, and for this case, the reliability of this switching process is assumed to be 100%. Also, for simplicity, the reliability of the system is calculated as if the redundant pumps are operating in parallel. Furthermore, experience in most chemical plants and refineries shows impending failure is usually detected and redundant systems are usually started in a timely manner to avoid lost production from the failing device. So assume no loss of production by use of redundant pumps. In this case, there are some initial acquisition type costs with the purchasing and installing of the parallel unit. That's a total of $17,000, plus the same disposal cost of alternative 1, that is $3,000 in year 10. The total annual costs come to $21,493. Alternative 3. Capital costs are $18,000 for a solar API pump, plus $3,500 for construction and installation, along with $1,000 for program management, $1,500 for engineering design, $1,000 for documentation, and $500 for technical data. Likewise, the plant maintenance organization will incur $1,000 for engineering documentation costs to put the equipment into the paperwork system, and $1,500 for training costs associated with the new class of equipment. Spare parts for the new equipment will be increased by $2,900 for a new set of seals and bearings. In this case, the capital cost in the first year is higher at $30,900, as this is a more expensive pump. The annual cost for this option is $44,444. Step 6, make cost profiles for each year of study. First, look at the first column, year 0. During year 0, that is the present time, there is capital cost that will be spent for the second and third alternatives. This comes directly from the non-annualized cost for the 3 alternatives. The non-annualized cost from that table is split into 2, the capital cost and the sustaining cost. The capital plus the sustaining cost will give the total cash flow for year 0. It is an outflow, so it's negative. Because the year 0 cash flow is already in the present value is the same as that of the cash flow. Then look at any of the remaining 10 years of the study. Line 1, there is no capital cost occurring during the 10 years of operation of the pump. Line 2, the sustaining cost in each case comes from the output result of the annual sustaining cost tables. Line 3, the depreciation is calculated on a straight line basis as 10% of the capital cost. Because there are no income allocated to these pumps, the profit before taxes are actually only a loss that is made, and thus the negative sign. It is in each case the total of the annual sustaining cost and the depreciation. Line 4. The company's profit is decreased by the depreciation. That means that the tax saving of 38% of that loss will be realized based on a 38% flat rate company tax. This is an effective cash inflow, and thus it is positive. Line 5. The net income is the total of the profit before taxes and the tax. Line 6. Because depreciation is not an actual cash flow, but just an amount by which tax reductions are allowed, it needs to be added back to accurately reflect cash flow. Line 7. The actual cash flow is then the total of the net income and the depreciation. Line 8. The discount factor as read off from tables or calculated. The discount rate in this case was given as being 12%. In the first lifecycle cost video, the formula for the present value was given. This is now transposed to the formula shown. The present value is the future value F for the year divided by the discount factor for that year. The discount factor for the year is shown as 1 plus I over 100 to the power of the number of years. A sample calculation is shown for year 5. Line 9. The present value of the cash flow of line 7, calculated by dividing the cash flow by the discount factor in line 8. All the present values for columns 0 to 10 is added together to give the value in line 10. Based on these alternatives, adding the NC pump in parallel looks more attractive based on the net present value at the 12% discount rate using straight line depreciation. No revenue stream is included in these calculations, so the case with the smallest loss will be the most attractive case. Step 7. Make break-even charts for the 3 alternatives. Break-even charts are useful tools for showing the effects of fixed and variable costs. The parallel NC pump cost line crosses the benchmark line for the solo NC pump in plus minus 1 year, so the costs are less for the redundant system after passing the 1-year mark. The solo API pump crosses the datum line in plus minus 5 years, and the costs are less than the solo NC pump, but the redundant NC pump system continues to have smaller costs and is thus more desirable. It has a lower net present value from year 1 onwards. Step 8. Construct Pareto charts of the vital few cost contributors for each of the 3 alternatives. Based on this, one can possibly change the cost of one or more of the alternatives and thus make it more attractive. We will use this information in step 9 following. Step 9. Prepare a sensitivity analysis of areas of high costs and take into account the reasons for such high costs. We first compile a table of critical information for the 3 alternatives. For each of the alternatives, we list the availability and reliability as calculated in step 5. Here we then simply estimate the values of maintainability and capability as being 0.8 in all 3 cases. Then they calculate system effectiveness by multiplying availability times reliability times maintainability times capability. Lastly, they list the life cycle cost of each of the 3 alternatives from step 6. Note, it is not clear what the definitions of maintainability and capability are. So one can just as well leave them out and come to the same conclusion. We then construct a graph of lifecycle cost versus system effectiveness from the table. The main point of the analysis is, first, the unreliability can be reduced by using a higher grade pump, that's the API pump, as shown, or the penalty of lost gross margin can be avoided by using a redundant pump, that's the dual NC situation. Many industrial organizations concentrate on small incremental gains of working faster, which feels good but isn't too effective, rather than using a smarter reliability strategy to avoid the breakdowns which are the root cause for loss of gross margins. The point here is that many, and the question is it not most, organizations are experts at emergency maintenance, that is working faster. But a better strategy is to work smarter by investigating permanent solutions to unreliability problems. In this case, it is just much smarter to change the pump configuration to a better one, so that a better reliability situation is obtained. One of the factors in the high cost shows itself in the Pareto analysis. First, the biggest cost in the case of the solo NC and solo API pumps is the lost margins suffered when the pumps needs to be replaced or repaired. In the case of the redundant NC pumps, there is very little cost margin. Then the highest cost concerns the cost of electricity. When comparing with the other two alternatives, it can be seen that the electricity cost is just as high. It was only partly hidden by the high value of lost margin in the other two scenarios. So there is then certainly a big opportunity to optimize on power cost in all three cases. Power consumed is a direct result of work performed, energy lost in inefficient motors or bearings, and energy lost in pump dynamics. Opportunities that come to mind are: first, energy savings by use of high-efficiency motors can save 2 to 5% of the total power cost, and choosing high-efficiency internals for the pumps can save 5 to 10% of the total power cost. Second, if pump internals were selected for 80% efficiency rather than the 70% efficiency used for the calculations, the power saving would be, as calculated as shown, $2,062.50 per year. This is about equal to all maintenance labor efforts spent to correct failures. The point here is that independent of the solution chosen for the reliability problem, by choosing the pumps correctly, one can save over $2,000 per year. This will, of course, have to be compared against the higher cost of higher efficiency pumps. That is, if there is a higher cost involved. But this shows how critical design or selection decisions in this area are. Step 10. Study the risks of high-cost items and occurrences. The failure rate data, or more correctly, the ROCOF, that's the rate of occurrence of failure data, in Table 12, is again sourced from Bloch, 1994 and 1995. There are quite a number of reliability databases where such data can be obtained. The calculation below illustrates how such data can be used to calculate the mean time between failures, the MTBF. Note, there is no data for the pump housings. In such a case, one must use own experience or other sources. One-stop shopping for the ROCOF is not possible. Step 11. Select the preferred course of action using lifecycle cost. The selection of a parallel or redundant strategy using NC pumps is the most attractive alternative out of the three proposed because it avoids process failure and thus reduces the high cost of unreliability. And one can further optimize the chosen solution by following the ideas developed in steps 9 and 10. Most of the values used in the analysis thus can be far better represented by the one or other statistical distribution. Most things in life can have more than one value. So doing a deterministic analysis like the one up to here gives you only one of a variety of possible answers. By implementing Monte Carlo simulation, one can optimize such solutions substantially. Failure statistics can be improved considerably utilizing available Bible distributions. These give better statistical representations for explaining the life and repair times for equipment. Bible failure database information is available. That's Barringer 1996b, to supplement earlier mentioned failure data from Bloch and Geithner. A partial listing of the Bible database is shown in Table 13. Recent papers describe how to put the Bible database information to work. That's Weber in 1996. Table 14 shows how Monte Carlo simulation works for the unspared NC pump. In section A, the variable values are used with random numbers to draw a random age to failure. For each of the pump components, values of beta and eta are chosen from Table 13. Let's use the seal as example. Using beta equals 1.4 and eta equals 3 years, and selecting a random number selected from the interval 0 to 1, one can then find the first failure time, in this case 0.23 years. This can be done through using the Bible function paired with the goal seek in Excel. The principle is simple, referring to the cumulative distribution function for the component specified by the values of beta and eta. The example curve shown here is not for the seal, it is simply presented to demonstrate the principle. The cumulative distribution function's y-axis starts at 0, representing the 0 probability of failure at the component's start of life. And it progresses to 1, indicated that all components of that type will eventually fail. Now, if one wants to simulate the life of such component, you simply have to choose an FT value between 0 and 1, and then read off the corresponding life on the x-axis. And to make it lifelike, one uses a random number generator to choose those values between 0 and 1. In the case of our seal, the x-axis will stretch over roughly 6 years. That is 2 times eta. So for the first iteration of our simulation, that's section A of the table, the first random number generated was 0.027 or 2.7%. Then using goal seek, we found the value of the failure time that would result in a value of FT that is equal to 0.027. That value of the failure time is 0.23 years. So the first failure will take place about a quarter into year 1. Then repeat the process to calculate the second failure time. We do not know how much it was, but it also fell in year 1. That is why there are 2 failures listed in year 1. The next failure only took place in year 4, and the one after that also in year 4. Then there was 1 failure in year 5, then 1 in year 8, and 2 in year 10. The summarized results are given at the bottom of table A. Referring to year 10, there was a total of 3 failures, 2 of the seal and 1 of the impeller. The total downtime was 24 hours from the annual sustaining cost table for the single ANSI pump. The times for seal replacement and impeller replacement are the same at 8 hours. Now this is a single run of the model. This is repeated 10,000 times. In our case, it states 10,002 times. So the figures of the 10,002 instances of the table A is accumulated in section B. So for year 5, as an example, the accumulated failures of the seal over 10,002 runs is 3,644, and for the shaft 465, and so on. The accumulation of downtime over 10,002 runs for year 5 is 80,022 hours, and the total number of failures is 9,540. In section C, the cumulative failures of section B are normalized on an annual basis by dividing each of the figures in section B by 10,002. This gives a totally representative annual expectation. Again, taking year 5 as our example, we can say that, firstly, we expect 0.364 seal failures on average in year 5, 0.046 shaft failures, and so on. Expected downtime in year 5 is 8 hours, and the total number of failures expected 0.95. In section D, we combine the figures of section C with the cost from the original table for this scenario, that is the single ANSI pump. The electricity cost is a fixed amount per year for this scenario. The cost of seals for year 5 is calculated from the original deterministic cost per year of $11,583 minus general inspection, etc. cost divided by the 0.33 probability of failure to give a total cost of $34,780 per seal cycle. This times the expected number of failures in year 5, which is 0.364, gives the cost of $12,660. At the bottom of this table, the general inspection, etc. cost is added. Now one can surely ask, Why spend the time and effort building such complicated analysis schemes? The answer is as follows. First, Monte Carlo simulations are more correct than the generalized and simplified data. Second, remember this scenario is built to teach and not to represent all real-world problems. Third, some guidelines. For Monte Carlo models, this question can now be asked, which is best, a large number of iterations or averaging the results from a moderate number of iterations? The answer, generally speaking, find the correct number of iterations by using the jackknife technique to study errors in the final results. So run 2 moderate-size iterations and compare the results by looking at the differences in the calculated numbers. Then double the number of iterations until the errors appear fairly small, and then double the number of iterations for the final run. Some general comments. Notice the number of seal failures and bearing failures are approximately the same, which justifies the usual good maintenance practice of replacing both units when either fails. Also notice the close agreement between the theoretical reliability and simulated reliability. Likewise, note how 1-year reliability values decline as the system ages, which parallels operating experience and common sense, but is often difficult to prove with numbers. The simulation shows availability drops slightly over the 10-year interval, but the number of failures approximately doubles due to system age. Consequently, the reliability plunges. This concludes our second session on lifecycle cost. I do hope this has enlightened the viewer. I thank you.